Welcome to session 3 in the series Analog Circuit Design using ADS. Here I'm going to cover, first revise what I have covered in session 2 regarding PN junction diode. And this PN junction, we started with, actually with the semiconductor, we started with the what you call intrinsic area density, right? Then we doped them, and then when we put them together, N and P type together, they form a PN junction, and then the charge neutrality is conserved here, right? This is because of diffusion current, which we talked about, and the Fermi levels lining up, right? So that's there. And this depletion depth minus W1 on the left side and W2 on the right side, they come to a stop when the diffusion current going this way. So if I consider diffusion current going this way, then that is being balanced by a drift current going that way, because what happens is this side gets so I'm kind of wrong here. So basically electrons are going this way, so that means that if electrons are going this way, then the diffusion current is this way, and then this sets up a field which is from the right hand side to the left hand side, and this results in a drift current which is going to be this way. And when these two currents become equal, that is the time when W minus W1 and W2 they get fixed, or depletion depth gets fixed, right? So that's what we talked about. Next thing we talked about was a relation known as Poisson's relation, right? And this was the charge density which we plotted here, and the area under the curve on left and right side are equal because of the charge neutrality, and this gives us the expression 2, NaW1 equal to NdW2. Now using expression 3 we integrated both the sides, and we find out what is the field. The field exists only in the depletion region, and the depletion region is a region which is devoid of the minority carriers. They still have the majority carriers, right? Now the left side field comes out to be as shown here by expression 4, and right side field comes out to be expression 5. This is obtained by for integration of left and right sides, right hand side of the equation number 3. Now at x equals 0, we from approaching from the left side, E max is the same as approaching from the right side. Okay, so that is this NaW1 equal to NdW2. That's why the E max is basically this quantity given by expression 6. So what it means is that the field intensity is the maximum at the epitaxial junction, right? And this is for an abrupt junction. For a graded junction, if it is going to be even higher, right? Next is we integrate it once more, right? So here when we integrate it, we have dou 2v by dou x, okay, will be equal to minus e. Okay, so now we integrate this again. Okay, after we integrate this again, we assume that the left hand side okay, junction is grounded, right? Now this is a p-type which is grounded. That's why we can assume this initial condition of 0 over here, otherwise it will be Vr, right? So the left hand side equation would be QNA over epsilon x square by 2 W1x plus W1 square by 2. Now this is going to be at x equal to 0, this is going to be V1, that is given by expression 9, and then the right hand side equation for voltage or potential is given by expression 8, and this will be on top of Vr in case there is a external potential applied, and then expression 2 gives V2, and the sum of the two is going to be built-in potential plus the external reverse bias applied. So that will be V1 plus V2. That will be equal to QNA W1 square by twice of epsilon and plus QND W2 square by twice of epsilon. Now this built-in potential can also be related to temperature and the dopant densities by this Vt, natural log of Na_Nd over Ni square. Now depletion depth is W1 on the left side and W2 on the right side. They are given by expression 12 and 13. Expression 15 gives the charge, whether you consider it from the left side or the right side is going to be the same. Okay, so this charge density, this is a total charge density, right? No, we multiply by, so this is the total charge. Okay, So this is given by this expression. Okay, now here I will draw uh, some more things which we discussed. One was the carrier density, right? And the other one was so basically, if I assume, let's do a carrier density here. Okay, and okay, so let's do the carrier density over here. The two sides of the junction, right, two sides of the junction are like this, and basically the carrier density is going to be, just one second, so this is x, and the carrier density goes this way, that it builds, it's for minority carrier it's 0 here, so this will be basically, this is the n side, so this will be pn 0, and this is approximately equal to uh, this is approximately equal to uh, okay, so basically ni square is equal to this, right? So ni square over nd, okay, and ni square over nd, right? And then if you go nd above, okay, so this will be nd above, right? So this will be approximately nno would be approximately equal to let me draw this again. This is doesn't look nice. Okay, I can do one more thing. I can just copy this one. Okay, so I can just copy this and paste this and just drag this up. Fine. So this nno is going to be approximately equal to nd, the doping density, and same thing on the right hand side. We have got np. So this is npo. npo is approximately equal to ni square over twice over na, ni square over na, right? So let me do this again, because I don't like this how it turned out. Okay, just one second. Okay, so this is going to be like that, and then okay, cut, just one second, bear with me, cut this out. Haruk, cut this out. Okay, let me draw this again. So this is like this, and then okay, okay, na is much larger than nd, so I'll go much higher than that. So this is going to be equal to, sorry, okay, so now this is going to be equal to na, and then ppo is approximately equal to na. Okay, so this is the carrier density. So let me just write it down here. This is, I'm talking about carrier density. So this is what we discussed last time, right? So this is the carrier density. Now the next thing which we discussed was what happens to the band gap, right? So I would just draw it here so that we have a, complete this thing. So if I consider this to be a conduction band, and let's consider this to be a valence band, right? So let me just draw this here. Okay, just one second, bear with me. Okay, so let's extend this over here, and then, sorry about that, and this, let's extend it over here like this, and let's extend this over here like this. Okay, so now okay, so now this is the conduction band on the p side, which goes up because the electrons have moved to this side, and then this is going to be the valence band on the p side. Okay, this is also moved up, right? Now what happens is that there is a Fermi level which is going from here all the way continuous up to here, I'd say. Okay, so this is a, let me draw this again. So this is the Fermi level, right? So EF. Then what you're going to have is you're going to have this lining up here. So this is your conduction band on the n side. Because it has lost electrons, the entire thing moves down, and this basically is like this. And let's talk about valence band on the n side. It's over here, let's say, and this is like this, and okay, so this is going to be your band diagram near to the junction. The Fermi levels line up, right? And this is because the electrons have moved from the left to the right, or there is a diffusion current from electrons have moved from right to the left, and there is a diffusion current from left to right, and which is being balanced by the drift current because of the field which is set up, and that the field which is set up is over here, electric field intensity E, right? So that causes the the drift current, and the equilibrium is at the depletion depth of minus W1 on the left side and W2 on the right side, and this is brought about by diffusion current being equal to the drift current, right? And the built-in potential is over here, V1 plus V2. So this is about a reverse bias diode. Now the next question comes is, where am I going to use this reverse bias diode? Okay, so reverse bias diode, okay, reverse bias diode basically has, okay, variable capacitance. So let's talk about capacitance across the junction. Capacitance. Okay, how do you get the capacitance? Okay, so to get the capacitance, all you have to do is take the charge equation, which is over here, 15, and differentiate this with respect to VR, right? So when I differentiate this with respect to VR, so just 1 second. So I am going to get CJ. CJ is dou Q by dou VR. Okay, so if I do that, I will just take the common term, the terms which are independent of VR outside. That will be twice of Q epsilon NA ND, right? That's what it is, divided by NA plus ND, right? And then differentiate with respect to VR, so that will be half of root of, right? So half of root of so this will be half of root of xi0 plus VR, half of root of xi0 plus VR, right? And we can take 2 inside, then we'll be left with twice. So instead of twice, the 2 will come to the bottom, right? Okay, or we can leave it as it is. Now at VR equal to 0, okay, VR at the condition of 0, this CJ0 would be equal to twice of Q epsilon NA ND divided by NA plus ND raised to half, right? And then there is a half here, and there is a 1 over square root of I0. Now if I substitute this in the first expression, you will have Cj equal to Cj0 divided by square root of okay, so basically Cj0, okay, so what you're gonna have is 1 plus VR by psi 0, because Cj0 has a xi0, so divide by square root xi0, so that's fine, correct. Okay, this is true for an abrupt junction, so I'm going to write this as 16, expression 16. This is capacitance. Now the capacitance is a function of reverse bias VR, right? We can write this as a forward bias also. This will be equal to square root of 1 minus Vd over xi0. Now this is asymptotic to asymptotic at xi0, Vd equal to xi0, and at that point the capacitance should become infinite, but this expression breaks down at, so this expression because this is based on a condition, right? The condition is that the charge is not leaking out of the junction. But when the diode becomes forward bias, when you go close to Vd, Vd equal to phi 0, when you close to that, then the diode becomes conductive, right? So it doesn't store the charge, so the capacitance should decline to 0. So expression, okay, so this basically, this expression holds, or rather it breaks down, okay, breaks down at Vd equal to xi0 by 2 roughly. Okay, so now let's draw this. Okay, so to draw it, so let's assume that I have a capacitance on this axis and I have got Vd on this axis, and let's extend this. Okay, so just 1 second. I've never moved a line before. That's kind of stupid though. Okay, that's fine. This looks better. Okay, so now what's going to happen is that this capacitance is going to behave this way. This is going to tend to become 0, because as Vd becomes negative and large, this would become ultimately 0. This is going to rise up. So somewhere at Vd equal to 0, we have got Cj0, right? And then it is going to, at xi0, this is going to become asymptotic. So at Vd equal to xi0, so this is Vd. At Vd equal to xi0, so this will keep increasing. Then, sorry. So let's make it clear. So what's going to happen is this is going to keep increasing, and then it's going to drop like this. And this is going to usually occur at xi0 by 2. Okay, so this is the maximum capacitance, Cj max. Okay, now so I substitute xi0 by 2 here, Vd equal to xi0 by 2 here, so I'm going to left with Cj max equal to square root of 2 of Cj0. Okay, now what happens is, if this is in case of an abrupt junction, right, so this is going to become asymptotic like this. Okay, this is in case of a abrupt junction. This will be 2 raised to m, 2 raised to minus, you can say 2 raised to m Cj0 in case of a graded junction, and this capacitance is going to be higher in case of a graded junction. Okay, so this we have a treatment which is based on assumption that the junction is abrupt. Okay, so this is what happens with the capacitance. So capacitance turns out to be a function of Vd, right? So if you forward bias the diode, the capacitance is going to keep increasing till Vd equal to xi0 by 2, and then the capacitance is going to draw back. Now this region which is from here to here, okay, this can be used as a voltage dependent capacitance. Okay, so this voltage dependent capacitance can be used in number of places. It can be used as a varactor, right? So it can be used in designing VCOs, which are voltage control oscillators, right? So that's one application of a diode, of a PN junction diode. Now the next application, so let's jot down the applications of PN junction. Okay, so applications. of p-n junction, and I'm talking about reverse bias, so we haven't yet looked at forward bias. Okay, applications of p-n junction diode. Sorry. Okay. Okay, so applications of p-n junction diode, right? Okay. One is it is used as a rectifier because it is obstructing the flow of charge when it is reverse biased, right? While it allows you to for the current to flow when it is forward biased. So we will talk about forward bias later on. So this is used as a rectifier. Okay. Second thing is a reverse bias diode is used for isolation of devices from the substrate. So usually the devices sit in the well, and the well is nothing but a p-n junction to the bulk. So basically, let's say a device sits in it well, right? So let's take an example. So that's a well. Okay, so let's consider a n-well process, right? So PMOS device is going to sit here in a n-well, right? And then there is going to be a okay. So what's going to happen is p minus over here, okay, and the device sits over here. So what you do is, so basically the device is going to sit over here. Okay, so this is going to be p plus, and the channel is going to be p here. This is going to be gate over here, right? And then source, and then drain. Then you can put in a body terminal here and plus, so this will be body, right? So this sits in its well, right? And then this p substrate is connected to the most negative, which is going to be 0 or ground. So this junction is going to be reverse bias. So this junction is going to be reverse bias. This causes the device to be isolated from the bulk, right? And even in case of n-well process, NMOS, again there is going to be a depletion region, which is because of the reverse bias. Is depletion region is going to isolate the device from the bulk. So this is used for isolation of devices. Okay, next it is used as a voltage dependent capacitance. Voltage dependent capacitor. And voltage dependent capacitor basically is used in your VCOs and all that. Okay, now another thing is in case of a BJT, okay, you have got two such p-n junctions back to back. So let's consider an NPN. So there is a NP junction, and this is going to be base emitter junction, and then there is a base collector junction, right, which is p-n junction here, right? So these back to back junctions, okay, they basically are their properties are going to decide the characteristics of BJT. So basically the injection efficiency over here, okay, of electrons is going to decide what is the beta, and then the what you call the base width modulation, because of the reverse bias p-n junction here on base collector, is going to decide your output resistance, right? So these factors are dependent on the characteristics of the p-n junction. So these are the applications of p-n junction. Now only topic which remains over here is a forward bias diode and a breakdown. Okay, so now there are two kinds of breakdowns here. Okay, so let's talk about breakdowns. Okay, diode breakdown. Okay, so why does the breakdown occur? Okay, so we go back to this one. Okay, if I apply a reverse bias, what's going to happen is this is going to still go down and this is going to go up. So now what's going to happen is this side is going to align with that side. So let's draw this again. Okay, so we're talking about breakdown. Okay, so we have this like this, and we go like this and like this, and we have like this, like this, like this. So this side, okay, and then we have got like this. This is the valence band, and somewhere over here, and like this. So basically this and this, okay, so when this lines up with that, so if you see here, sorry, what happened to my diagram? The entire thing is gone or what? Okay, so I'm gonna save this. Okay, so what happens is the following. So when this lines up with that, right, if this depletion depth, okay, is small, this usually happens when the doping is high, when doping is high. So when this happens, there is going to be a tunneling. So these electrons are still going to move this way, and there is something called tunneling here, right? So this is known as Zener breakdown. Okay, now when they are far apart, so when this is not small, okay, what is going to happen is the electrons, okay, they gather over here, and these electrons, they keep on, okay, accumulating energy till they are going to be, so basically, so if I do a negative, so this side is going to be negative and this side is going to be positive, right? So I'm basically pulling out electrons this way, so I did a mistake here. Let me correct this. Okay, so there is a tunneling, so this is a leakage current, right? So there is a tunneling of electrons this way because they are attracted. Now these electrons, if the distance is large, they cannot tunnel through, so in this case they accumulate over here. So when they accumulate over here and you keep on increasing the reverse bias, they are going to generate these electron hole pairs, and these electrons are going to lose energy this way, and then they are going to come this way and they are going to combine here, right? So and they are going to be pulled out by a positive terminal. So if you take this route, right, this is going to be thermally dependent. So whenever they go down in potential, they are going to lose their energy here, and that would be like heat, and this will cause more electron hole pairs to be created on the left hand side. Okay, so this would be called a avalanche breakdown. So they say that if you have a hyperdoped diode, then it's going to see a Zener breakdown, which is temperature independent more or less, and then if it is doped less, right, so if the doping is less, then it is going to see avalanche breakdown. Okay, so this is about the breakdown. Okay, so now let's see what happens if I forward bias. So if I forward bias, this movement is going to be different in the different direction. If I forward bias, it will go this way, and this energy band diagram will go this way, and then EF or Fermi level will distort here, right? Okay, so now let's draw the carrier concentration in a PN junction. Okay, let's draw a carrier concentration in a PN junction very near to when it is turned on. Okay, so this has shrunk a lot. Similarly, the other side has shrunk a lot. Okay, next is I'm going to draw the carrier densities here. Okay, so this side, if you remember, this side is going to be electrons, and because they are forward biased, so they are forward biased, so there is going to be a slope this way, and these are majority carriers on the other side. Okay, and similarly you have got over here, and they will also go this way, and it is going to drop in like this to a minority carrier this way. Okay, so now this is going to be, sorry, this is going to be PNO, and this is NN, NNO, and this is PPO, and then NPO. Okay, so these are minorities, so they are Ni square over Nd, Ni square over Nd, and this is going to be approximately Nd, this is going to be Na. Okay, so now what is the source of this current? Okay, or rather it is the reverse way. The current causes these slopes, so basically these slopes are indicative. So let's say there is a point which is minus ln, where the excess electrons basically become equal to the bulk, and similarly over this side there is LP, where the same happens. So now the Fermi-Dirac relationship, okay, gives you the density at x equals 0. So let's put that. Okay, so densities, we'll blow this up, so you can consider this to be like this, and over here, sorry, okay, so here it is minus ln, and this is equal to Ni square over Nd, and this side it is going to be NPO, which is again Ni square e raised to Vd over Vt. Okay, so this is a Fermi-Dirac relationship, right? So let us find out the slope. Okay, so the current is proportional to this slope of minority carriers, right? So let us find out so this is going to be electron current, right? So this is going to be electron current. Electron current would be equal to QA. Okay, I'm basically ignoring all the signs. Okay, I know what will be the direction of current. So QA d, okay, QA dn dou nx by dou x. There will be a minus sign here, but minus of the charge would cancel it out. So I'm just ignoring the signs. So this will become QADN, and this is going to become NPO e raised to Vd over Vt minus NPO divided by 0 minus ln. So what will be there? It will be ln. So this will be equal to QADN Ni square, okay, QADN, okay, so NPO, okay, Ni square over Na ln e raised to Vd over Vt minus 1. So now this minus 1 is because of minority carrier here. So this is like a leakage current, right? So had this NPO been 0, that leakage current would have been 0, right? So you remember where this is coming from. This is coming from minority carriers drift current, right? So similarly you have got IH is equal to QADP, dou, you will be like P x by dou x dou, okay, so in that case PNO Ni square over Nd, okay, LP e raised to Vd over Vt minus 1. So the total current would be equal to I electron plus I hole, that will be the total diode current, will be equal to QA Ni square over, yeah, QA Ni square dn over Na ln plus dp over ndlp times of e raised to Vd by Vt minus 1. So this can be written as Is e raised to Vd over Vt minus 1. Okay, so this is going to be the diode current, where Is is this term. Okay, so this term is Is. Okay, so now we know what is a diode current, right? Diode current has a exponential relation to the diode voltage. Now if I do that, I can say that e raised to x can be represented as a Taylor expansion as 1 plus x square by 2 factorial plus x cubed by 3 factorial and so on, right? So notice that I have this x square, so this becomes non-linear. Okay, because of this non-linear nature, if you have two uh, let's say cos of omega 1 t as one signal plus cos of omega 2 t as the second signal, so if this is x, then the x square and x cube will result in the mixing of these omega 1 and omega 2. So this would result in, so if I consider the even order mixing over here, right, so this will be component omega 1 plus omega 2 and omega 1 minus omega 2 generated. So this is called mixing, right? So this is usually used in a mixer, right? So mixer, so diode can be used as a mixer. So one of the application of a diode which we are jotting here is fifth one is diode can be used as a mixer because of its non-linear relationship between voltage and current. So I guess with this we come to an end of what a diode is used for, right? Now in the next session I'm going to go to MOSFET, right? So I'm going to just save it, and I am just going to stop here.